All right. Hello, everyone, and welcome to Lecture 5, Structural Design. Last week, we started the discussion about design of columns. Do you remember what we did last week? Yes, it was design of a column under axial load, and we realized there are mainly two factors that will contribute to how much a column can take. The buckling capacity, which is what is the maximum load you can put on a column before it fails in buckling. This is very sensitive to the height, to the length of the column. Taller columns, they have significantly reduced capacity. If the column is short and the dimension of the column is stiff enough, then the governing factor will be like the axial stresses on the column. The material strength will govern. Okay, so remember what I said about the possibility of a column to be exposed to moment. If you're designing a column, what are the forces on a column? Is it just axial load, or you can have a case when you have axial and moment on the column?
Axial moment.
Yes. What would introduce a moment on a column?
Crane method.
Crane? How would a crane introduce moment on a column?
A moving crane that which
Yes, I actually have a picture exactly of that. So this is a column, and if you look closely at the joint above, this is a very big, significant joint, because as a matter of fact, this is designed as a portal frame. So as we discussed in structural analysis too, you can have a frame resisting gravity load, and it will have moments in the column. So this column will be designed for axial load and moment. To add to that, if you look closely at the connection here, somewhere along the length of the column, there is a corbel or a short cantilever supporting a longitudinal beam. This beam is going to support a crane. So there is additional load acting on this short cantilever. This introduces moment to the column as well. Do you have a question? No? All right. So can you think of any other case where you can have moment in a column? Yes, if it's exterior column. So for example, this column here, these columns, this is the outside of the building. So when it's finished, there will be like probably windows or just solid walls sitting on these girts or on these beams, and the wind load will be transferred to these horizontal beams, and they will transfer the load to the column as a point load. Or the span of the window or the wall could be sideways, so it could have a uniform distributed load on the column. Long story short, if you're designing the column on the outside, you will need to account for the wind effect. And this column becomes like, it's called beam column, or a column that has axial load and moment. So today we will talk about how to design a column that has axial load and moment on it. There is a third and very common reason why a column could have moment, even if it's not exterior column or it's not a portal frame or supporting a crane beam. Curious if you can think of this. I have few diagrams here that could help you. Can you think of a reason why a column could be exposed to moment under the axial load? If the axial load is not applied perfectly in the center of the column, it's applied with an offset or eccentricity. As a matter of fact, most connections will have like the bolts offset from the face of the column. The weight of the beam is transferred through the connection at the bolts. So if you look closely here, the bolts and the connection is usually like offset from like the face of the column, and the face of the column already has a distance from the center line of the column. So this eccentricity, this distance, multiplied by just the vertical reaction of the beam will create a moment, an additional moment on the column. So this column, if it has axial load and the axial load is not applied at the center, this column is going to be experiencing axial load and moment. So this is another way of looking at it. You can have a column, a vertical column. It has like an I section, and framing into it, this is a plan. You're looking at the plan view of the column. A beam could be framing to the web, or it could be framing into the flanges. In either case, the weight of the beam is going to be applied at an eccentricity, E, from the center line of the column. And we will use the vertical load from the beam calculation, the reactions of the beam calculations, multiplied by the geometry of the connection. How far the bolts are going to be from the center line of the column, and we calculate the moment on the column, and it could be in both directions. Do you see how the eccentricity could be in both directions of the column? So let's take a look at this cross section here. The strong axis is about x. The bigger moment of inertia is about x. The smaller moment of inertia is about y. So if you have a beam framing in the along the x-axis, the beam with the eccentricity will create moments about y. And if there is a second beam framing in the y direction, it will create a second moment about the x-axis. Can you visualize a cross-section that is exposed to moment about x and moment about y? Does that make sense? How would a section resist moment in two directions? Squared. What do you mean squared?
The cross-section of the column is squared.
If it's squared, well, how about if it was like a white flange or an I section like this?
One of them will be stronger.
Yes, one side will be stronger, but is it possible that a section would be under a moment about both directions? Yes. If this column has a beam from the x-axis and a beam from the y-axis, this will create a double moment on the section. All right. The next thing we talked about was the effective buckling length. So let's say that we have a column that is spanning like a double height, like 7 meters or something like that. 7 meters is like 2 floors. What's kind of the average height of a floor? 3 meters, 3.5 if you're like creating a bigger space. So 7 meters, this is a pretty tall column. If you go through the calculations we did last week to calculate the axial capacity of a column of 7 meters, you will find that there is quite a bit of a reduction because of buckling, because of the tall length. A way to help that section is to brace it with lateral beams.
Decrease the effective length.
That will decrease the effective length. All right? So let's take a look here at the buckling length. If the whole thing is 7 meters, the buckling length with no side beams, which direction is the critical buckling direction? Is it outside, like about y, or about x? For a column that has no beams framing into it, when it buckles, about x, is it gonna buckle about x, or is it gonna buckle about y? Like, is it gonna buckle in the x direction or in the y direction?
We use the diagram in the right.
This one here?
The one in the right.
I'm talking about the single column. About what? So it will move like in the y direction? Oh, it will move in the x direction. How do we judge? How do we answer this question? Obviously, the column is gonna want to buckle. It wants to buckle in the weak direction. What is the weak direction? How do we know if this column is weaker in the y or weaker in the x? We get it from the moment of inertia and from the radius of gyration. So typically, the cross section is stronger in the direction of the web. It's very unlikely that this direction will be stiffer than this direction. That's why the column wants to buckle in the XZ plane. Does that make sense? Because you're gonna design the column for like the most critical direction. The most critical direction will follow the smaller moment of inertia or radius of gyration. Okay, this is an interesting case because we have the buckling length in one direction, it's different than the other. So how do we get the effective buckling length in the second case over there? So the first case is like a column like this. This is actually a test in the lab. You put the column, you define the support conditions, the pin, or fix, and then you apply load on it to verify the code equations. Like we should be able to test the code equations and see if a column like this, what's the failure type or what's the ultimate capacity for it. So it will start to buckle in the weak direction. These are the flanges and it will buckle in the XZ plane. So I need you to think about this for a second. Tell me, what is the unsupported length or the effective buckling length for a column that is supported at mid-height at point C in the XZ plane? What is the buckling length about X and what is the buckling length about Y? And when I say about, I mean which moment of inertia will resist that buckling direction?
About Y, the full length, about X, the half length.
About Y, the full length, about X, half length. So about Y, is this in XZ plane or in YZ plane? Do you see what is the YZ plane? The YZ plane is the plane of the web. So this is the cross section of the column. Let's call this the Y axis and let's call this the Z axis. Perpendicular to the wall or to the board is the Z direction. So the buckling, if this column is going to buckle in the XZ direction, is this the side that is braced or is this the side that is full height? So the layout of the column, the web is in YZ plane. So that's the web in the YZ plane. Where is the beam? Is the beam parallel to X or is it parallel to Y? In the figure on the left.
Parallel to X.
Parallel to X. What makes you say that?
عارف النص.
Yeah, because there is a beam here connected to the column, parallel to X, and the location of this beam is at the mid-height of the column. So, is the effective length, effective height of the column, when it's buckling about Y, meaning like in the XZ plane, is it the full length or the half of the height between the beam and the supports? When it wants to buckle in this direction, the dotted line. Do you see how at mid-height the buckling of the column wants to kind of shift it? Half. Yes, that is the correct answer. Because when you look at this diagram in XZ direction, the buckling is restrained at the lateral beam. But because of the Y direction, there is no beam, the buckling length is the entire height of the column. column. This is very important to consider. You are expected to encounter a case like this. The column is restrained in one direction at mid-height and is not restrained in the opposite direction. So you will need to choose the correct unsupported length with the corresponding properties of the cross-section. There is another factor that you need to account into consideration, which is the condition of the support. What type of support do you have? Is it pin? The effective height is going to be the actual height multiplied by an effective length factor. So how do you know if the connection between the column and the beam is pinned or fixed? Any guesses? How do you tell if the connection? What's that? It comes from the actual design of the connection. If you look at the connection to the left, you'll clearly see a gap between the flanges of the beam and the column. So it's supported like in the center line of the beam. This typical connection will allow some rotation. On the opposite side, look at the left side connection. The bolts are on the top flange and the bottom flange, and the bottom flange is actually stiffened. It's actually deeper than the beam. There are additional stiffeners all welded to this plate, and the plate is bolted to the column. This connection is fixed, so that will affect the laterally unsupported length for the beam and for the column as well. A column that is fixed with a beam will have a fixity condition. If it's pinned with the beam, it has a pin condition. So what's the influence of the support type on the unsupported length of the beam? Fixed support will make the unsupported length shorter. That's why for fixed, you reduce actually the actual length. For pin support, use the exact actual length. The effective length factor is 1. That means you take the actual height as the length, the buckling length of the beam. If your column is fixed, you can reduce the height, which can help your section. So let's say you have a column and you're struggling to get it to take the load. If you change the connection to fixed, there is a chance that you can increase the capacity of the column. Does that make sense? So this will make sense if you're in a situation that you're trying to get a connection to work, or you try to get a certain section to work. You can play with these variables. You can introduce a beam at mid-height. That will change your buckling length completely. You can introduce different fixity from pin to fixed. That will change it as well. All right, so let's take a look at how the Eurocode suggests we design a column like this. There are basically 2 ways to look at this. The Eurocode suggests few methods that are very detailed, and they have these factors KYY and KYZ and KZZ. They depend on certain parameters, and it's time consuming to calculate them. So there are supplemental documents to the Eurocode that introduce a simplified interaction criteria for the design of columns. So let's think about it for a second. How do you make sure that a column that has axial load, moment about X, and moment about Y doesn't fail? How do you design something that has these 3 straining actions acting on the same time? Can you develop the full axial capacity of the column and the full moment capacity about X and the full moment capacity about Y at the same time? Can you compare the loads to the maximum capacity in all directions? 3 combined, okay. So how are you going to make sure that the section doesn't fail? Do you design it only to X and then see if it fails or not, and only to Y, see if it fails or not, and only to axial, and see if it fails or not, or you combine the three. Okay, how would you do that? How would you check a section that is subjected to 3 different straining actions? This is a very interesting concept. When you have a cross section, let's say it's rectangular like this. A axial load or the normal force on the column will result in stresses. The axial stress equals the force divided by area. So you can say it's more or less uniform. There is a uniform compression stress that equals the axial load divided by the area. If this is the x-axis and this is the y-axis, let's have a moment about y and a moment about x. This is moment about x, and this is moment about y. The moment about x will cause compression at the top and will cause tension at the bottom. Does that make sense? We talked about the moment stress distribution due to moment on a cross section before. The tail of the arrow will cause tension, the tip of the arrow will cause compression, and this compression, this stress here, will add to the axial compression. So in a way, that corner over there is feeling the axial stress from the axial load, and on top of it, the moment is stressing it even further. And if you do the analysis for My, you get another similar diagram with compression at the tip of the arrow and tension at the tail of the arrow. So you will find that moment about x and moment about y and axial load, you add up all these stresses, and that will be like the worst case scenario. That corner is resisting moment about x and moment about y and the axial load. The opposite tip or corner is feeling the tension side of the moment, so it's not as critical. Having said that, you need to make sure that the material is not going to fail anywhere. And that's why you introduce this, some codes call it like a unity equation. You make sure that the ratio between the actual normal force compared to the capacity, the axial capacity of the column, you add to it the actual moment divided by the capacity of the section in moment about y and about z is less than 1. So that means that each direction of action shouldn't exceed its capacity. Axial load shouldn't exceed the axial capacity of the column, same as moment in 2 directions, and you add them all together and make sure it doesn't exceed 1. So does that mean that I can apply an axial load that is very close to the full axial capacity of the column? No, why is that? There you go. It's not going to leave enough room for the column to resist moment about x and moment about y. That's exactly why. Excellent. All right. So how do you calculate these factors? What are the top factors here on the column? The Eurocode has this interesting symbols. E is the effect of the load. So you calculate the self-weight, you calculate the live load, and figure out the load on the floor, and then from the load on the floor to the load on the beams, and from the reactions on the beams, you get the axial load on the column. You get the dead load and live load, and use the factors to design an ultimate limit state. So the factors on the top are the actual factored normal force, the moment in x and moment in y, or the axial load multiplied by the eccentricity from the connection. Remember what we talked about? The reaction of the column is not applied at the center line of the column. The reaction of the beam is not applied at the center line of the column. So this distance will introduce the moment about y and about z. All right, so how do we calculate the bottom factors? The bottom factor for the axial load, B is like for buckling. This is the resistance of the column for buckling. That's very similar to what we did last class. Do you remember what we did last week? We got the axial capacity of a column due to normal load. And we calculated this already. So you can use like the calculations from last week. The capacity for bending about y will take into account the lateral torsion buckling. Do you remember when we designed beams, we had to decide, is the beam laterally restrained or unrestrained? So what would restrain laterally a beam? If you're designing a beam and slab, if you connect the slab to the top of the beam, it's going to prevent it from lateral torsion buckling. What about a column like this? Or bracing, yes, 100%. So what about a column like this? Just like a column that has nothing attached to it. Is this column laterally restrained or unrestrained? Unrestrained. So you will design it as if it's a beam that is laterally unrestrained. That's why you will find the factor that you compare moment about y has the buckling in it. You don't have to design the moment about z for buckling because the buckling usually is in the weak direction. So you will consider the lateral torsion buckling in the direction about y, or in the strong direction. In the weak direction, you will just consider the moment capacity of the section. These factors we've dealt with in the moment capacity, the lecture when we talked about the moment capacity. You should go refer to it to get these factors. What's the partial safety factor? What's the plastic section modulus? And F yield, how do we figure it out? And we will need the reduction factor for lateral torsion buckling in the Y capacity. So before we go into the equations and how we get everything, do you understand how to design a column with axial load and two bending moments? This is pretty important. Like you can expect an example like this. Before we leave this, can I get someone to summarize what I've been talking about? How do you design a column under double moments and axial load? Think about the examples I talked about. Think about what I said about this equation. What would you do if you were hired to design a column under double moment and axial load? Any volunteers? How would you design? What's that?
I have a question.
Okay, go ahead.
Are columns coming in the midterm?
For the sake of the midterm, it's going to be very similar to the mock test. So just make sure you solve the mock test and the final will be very similar.
So it's just gonna be one question?
I would say similar to the mock test. Just like go through the mock test. The exam will be very similar. Something that would fit in 30 minutes. The exam is 30 minutes.
So what is not coming?
I will leave you to the mock test.
So that we can study that for the mock.
Yes, okay, all right, I see what you're saying. So 30 minutes is not going to have a lot of time to go through a whole bunch of things. So prepare up to the area relative to the mock test.
So only beams.
So when is the mock test? Is it this week?
Sunday week after.
It's not next Sunday, the one after.
Yes, okay, yes, you're right. So probably it's not going to track all the way to the to week 7. So a good reference would be just like the mock test. Like if you prepare the mock test, you're gonna be good to go. Does that make sense? So back to my question. Can someone summarize how to design a column under axial load and double moments?
جمعهم على بعض ولازم تبقى less than 1.
Yes. So what are you gonna add up together?
Moments.
Okay, the actual moments on the column?
المومنت direction اللي عندي is z وال y.
About Z and about Y. Okay. You're gonna add just the moments?
The moment over the capacity.
لا moment.
Yes, you add the ratio between the moment and the capacity. The actual moment and the capacity in that direction. And then you add to it the actual moment and the capacity, and then you add to it the actual normal force and the capacity normal force according to this equation. So you will have to multiply the Z direction by 1.5. All right? So it's very important to refer to the actual equations in the code. I need you to have your own version of the code because codes are going to be eventually updated. So you need to be familiar with how they work and work your way around it. I just want to point out that this equation is in a supplemental document. It's a document that comments on the Eurocode that simplifies a little bit the calculation of the K factors. So when you go look for it, look for this document. It's the verification of column in simple construction. All right, so this is all something we covered when we designed beam under moment with lateral torsion buckling. We will need this for the example. So the notes will tell you in order to get the moment capacity for the moment considering the lateral torsion buckling, you need to get 4 things pretty much. Gamma is a partial safety factor and it equals 1. So that takes care of gamma M1. The F yield, we've always used it because you limit the capacity compared to how much is the ultimate stress of steel. So F yield is going to be almost in all the formulas. And that leaves us with like basically two factors. Do you know what WY is?
Section modulus.
It's the section modulus. It's the ratio between the moment of inertia and the height divided by 2. It has to do with the geometry. So which section modulus do you use? Use it in the strong direction with the moment that is in the strong direction. It's very important to choose the correct section modulus. Do you see how this section, when you go in the commercial tables, it will have 2 W's. W about X and W about Y. One of them is stronger than the other. If you have this beam, it's gonna deflect less in the strong moment of inertia. If you kind of move it 90 degrees, with the weaker moment of inertia, you get more deflection, you get more buckling. The section is weaker or less stiff in these directions. Okay, so that will leave us with the reduction factor for the lateral torsion buckling. And all these equations just to get how much do we reduce the capacity of the section. The exam is open book, so you can work your way the steps to how to calculate these factors and have like all the equations you need. So you have a process. You understand what you need. I need the capacity of the section in moment. All right, that's the equation. Most of the factors I know, I will just need to spend some time to calculate the reduction factor. So the reduction factor depends on lambda and depends on imperfection factor that we can get from the tables over there. And depending on the shape of the cross section, the code will suggest which buckling curve do we use. So it's very important that you go through the design process and figure out what you're set for yourself. What are you gonna do when it's time for you to design? Let's say like this is like the final and I give you a column. don't make it like a surprise for yourself. Oh, it's an open book test, and I will figure it out when the time comes to it. You need to work your way through it and make sense of the process. Familiarize yourself with the factors. So when it comes to the application, you don't get lost with all these symbols. As a matter of fact, it's a great thing that we have the code to facilitate the design for us. It pretty much guides designers and engineers how to do it. If every engineer would have to come up with their own way, like that would involve a lot of uncertainty, there would be a lot of inconsistency in the industry, and it will put a lot of enormous responsibility on your shoulder if you don't have a guide how to design. You would maybe you were referred to like analysis or results from experimental results. You would go to textbooks. So anyway, we're grateful that we have the engineers that came before us that created all these equations, despite that they might look confusing at times, but it's actually to pave the way to make the design process more reliable and more consistent. There is a factor in the equations in the previous slide that depends on the ratio between the actual bending moment and the uniform bending moment. This is to account for a column that has wind load in between both ends. If there is only moment from the eccentricity, the moment diagram will be linear. So if you have anything other than linear bending moment, you will probably need the C1 factor, and the code equation tells us how much is C factor that you use relative to the fixed support, to the end conditions, and the load pattern. For C1 to be equals 1, that means the moment is linear. There is eccentricity at the top, and maybe there is no eccentricity at the bottom. The moment diagram is linear, and you don't need any of that. If the moment is just due to eccentric axial load, the moment diagram will be linear, and then you're not going to need this slide. This is the normal capacity, including the buckling effect. We got that from last week. We did that last week, how to calculate the axial capacity of the column. All right, so that pretty much leaves us with an example. Let's say you're part of a project, and a fellow engineer did the load takedown, calculated the self-weight live load, and gave you reactions of beams. And your job, your task, was to design this column that has 3 beams framing into it. Can I get your thoughts? How would you start solving this problem? What are the forces you need to design this column for? Is it just axial load, or you take axial and moment as well?
Axial and moment.
Why is that?
Because you need to account for the rotation.
Which rotation?
عشان في
All the beams that are connected to the section.
Yes.
في main beam secondary.
Yes. So how the main beam and secondary beam would cause moment on the column. Any thoughts?
The eccentric not connected directly on the center.
Yes, because the connection of the beam with the column is not right at the center line of the column. It's offset at the bolt location. So we will consider the reactions. The problem already gave us the reactions of the beams due to dead load and due to live load. We will account for some eccentricity because of the connections, and that will introduce axial load, bending moment about X, and bending moment about Y. So what would you consider the effective height of the column? What would be the effective height of the column? Just take a look. Let's say this is a problem in the exam. What would be the effective length of the column?
4.5.
Okay, the whole thing is 4.5. But top connection is pinned, bottom connection is fixed. So how much is the effective height of the column?
What is the factor for the pin fixed?
For pin fixed. So you need to, that's very important. You need to look at what is the base connection type and the top connection type, and then you use the effective length factor corresponding to this case. If it was pinned at the top, pinned at the bottom, the factor is 1, so you will use the actual height as the effective length. So the actual height is 4.5. Because it's fixed at the bottom, pinned at the top, you will multiply that by 0.85. That's the factor for fixed pin. All right, so now we know the effective length of the column. What do we do next? We need to choose a section, like a trial section, so that we can see what's the capacity of that section and does it fulfill this equation or not. So you go to the commercial tables, pick a section, and that will give you the moments of inertia, will give you the section modulus, and the modulus of elasticity and G. These are constants because they're not going to change. They depend on the steel property. So you get them from the code. The code will tell us how much you use G and how much you use for E. And then, how do we make sure that this equation is satisfied?
Less than 1.
Yes, you start calculating the actual forces, and then you start doing the actual capacity. Each one, you refer to the code equations, and once you figure all that, you bring it to this unity equation. Unity means like, when you add all the factors, it shouldn't exceed 1. If it exceeds 1, it's overstressed. It's too much stresses for that section. So what happens if you realize that the stresses on this section is bigger than 1? What would you do?
Choose a bigger.
Yes, you will have to choose a bigger section and make sure that this, all the properties, when you plug them into the equations, they are safe enough to take the load. So, if you choose a section and it turned out to be like 0.5, when you add all the sections, it's 0.5. Is this an acceptable design, or do you need to change the section?
That's accessible.
Yes. Why?
I don't know.
Because it's less than 1. Any other thoughts? If you realize when you add all these factors, it's 0.5.
Maybe we find a more efficient or more economic.
Okay, yes. You're absolutely right. It is not going to fall. Actually, it's way too strong because you're using only 50% of its capacity. It can carry more. So maybe you could save your clients some steel, save them some money, and use a different section that will be more effective. That will be more effective. Does that make sense?
Section.
8.5? So what would you say? How would your section be effective? Do you want the stresses to be way less than 1
No.
or closer to 1?
Closer to
So,
1.
yes, why?
هنختار bigger section or the
You
same section?
you choose bigger section if the stresses are too high and it's more than 1.
Okay.
If it's very small, like 0.5, you're using 50% of the capacity, then this section is not very economic.
Okay.
All right? So at the same time, I don't like to push the efficiency to like 0.999 because that usually doesn't leave enough space for the connections. The connections will take some of the geometry of the column, and they have their own capacity as well. So don't stress out the column or the beam too much, and when the designer comes to fit the connections, it's unsafe. So I would say 0.9, 0.85, that's reasonable. All right? So let's take a break and let's do that example in the tutorial. If you have any questions, please come see me. If not, I will see you in the tutorial. All right, see ya.